In our last video, we learned how to use a simple model to think a little bit about how the atmosphere may affect the temperature of the Earth by interacting differently with radiation in different regions of the electromagnetic spectrum. Now let's spend one more mini lecture exploring some of the things we can do with our heat balance equations. One common argument that you'll hear from people who are skeptical of the claim that increasing carbon dioxide in the atmosphere will lead to increased surface temperatures is that carbon dioxide is already absorbing as much heat as it can. It's saturated. Here's a typical example of that claim on the web. This one from the site of, quote, independent scientist Gary Novak's. The argument is this. All of the radiant energy leaving the Earth that CO2 can absorb has already been absorbed. Thus, doubling the concentration of CO2 will not allow for more energy to be absorbed. It'll just all be absorbed a little lower down in the atmosphere. This seems reasonable. For example, imagine a fish tank full of water with a light behind it. Let's say that we add a dye to the water, and that dye absorbs light. Maybe the dye is octopus ink. We keep adding this dye until we can no longer see the light behind the tank. How much less light will we see if we now double the amount of dye in the water? Well, no less light, obviously. We'd already absorbed all the light that it was possible to absorb. In truth, the dye probably won't absorb all the light at any concentration, but instead the effect of adding more will progressively decline as we get more and more dye in the tank. When adding more dye makes very little difference, we say that the effect has saturated. Our previous model was an attempt to describe an atmosphere that absorbed all of the incoming long-wave radiation. What would happen if we now added more greenhouse gas to this model that should, according to Novak's argument, be saturated? Well, we can approximate that by adding another layer just above the first one. Let's say we double the CO2 from what we had before, so the new layer acts exactly like the old layer, absorbing whatever long-wave radiation hits it, but it's transparent to solar shortwave. We'll check to see if the new temperature stays at 30 degrees Celsius or not. So, to create our model, we draw the surface again, and this time we have two atmospheric layers. I'm going to do one more thing that a lot of you won't like, but I think it's going to simplify my drawings a fair amount. Remember last time we kept having to keep track of the reflected energy E sub t times b, as well as the fact that we essentially block energy as a circle and emit it as a sphere, so we have to always write the factor of 4, and then E sub t times 1 minus b divided by 4 kept showing up all over our equations, and it takes forever to write. Well, now that I understand where that term comes from, I'm going to simplify by assuming that all of that bouncing and geometry gets dealt with first, before we even get to my drawing. And from now on, I'm going to just worry about the incident energy that I care about. So I'm going to write E hat sub t, which is equal to E sub t times 1 minus b divided by 4. And you might remember from last time that that's just 239.2 watts per square meter. Now you don't have to do it this way. You'll always get the same answer if you keep track of albedo the way we did in the last video. Plus, if you want to model an atmosphere that absorbs in the short wave, for example ozone does, and include some surface albedo, then you'll need to draw it in all explicitly and so on. But for the models that we'll do today, this is going to be fine. Okay, so we drew E hat sub t coming in at the top of what is, from the perspective of the surface, the second atmospheric layer. That atmosphere doesn't absorb any shortwave radiation, so all goes through and makes it to the first atmospheric layer. Again, doesn't absorb any shortwave, so that continues to the surface. Like before, the surface heats up and emits to the first atmospheric layer. There, all of the energy gets absorbed, so nothing makes it through. The atmosphere warms up and emits the same amount up as it does down, and we'll call that EA sub 1 or E sub A1. That is long wave radiation, so when it hits the second layer, it all gets absorbed. Now the second layer heats up and emits, and we'll call that E sub A2, and draw that going up as well as down. We've added a new variable, E sub A2, but that's okay because, as you'll see, we've added a new equation as well. Like before, we start at the outside and work in, only caring about what's coming into or leaving the layer that we're focused on at one side of that layer, the top side. At the top layer, we have E hat t equals E sub A2, and that's all. The second layer, we have E hat T plus EA2 equals EA1. At the surface layer, we have E hat T plus EA1 equals ES, so let's solve for ES. From the first equation, we see that EA2 is just equal to E hat T, so we'll plug that into the second equation, giving us E hat T plus E hat T equals EA1. So EA1 is 2E hat T. Plugging that into the third equation, we have E hat T plus 2E hat T equals E sub S. So E sub S equals 3E hat T. Now that's interesting. Notice that with no atmosphere, we just had E sub S equals E hat T. When we added a fully absorbing atmosphere, we got E sub S equals 2E hat T. Now that we have two atmospheric layers, we have 3E hat T. It turns out that this doesn't end. Every time we add a layer that's fully absorbing in the long wave, it's like adding the energy of another whole sun to the surface. We can calculate it out, and we see that if Earth had two fully absorbing atmospheric layers, the surface temperature would be 335 Kelvin, or 62 degrees Celsius. Very hot. And this idea of greenhouse gases continuing to warm the planet even after they've gotten crazily thick isn't just theoretical. The space-measured temperature of Venus is actually really low, 44 below 0 Celsius, because of its high albedo. However, the surface temperature of Venus is about 465 degrees Celsius, which is 870 degrees Fahrenheit and 735 K. Why? The Venusian atmosphere is over 96% carbon dioxide, and it's so dense that pressure at the surface is about the same as it would be almost a kilometer below the ocean's surface on Earth. So Venus packs a lot of greenhouse gas into its atmosphere. Turns out it's the equivalent of about 100 fully absorbing atmospheric layers. In fact, Venus experienced a runaway greenhouse effect early on in its development, where the temperature got so hot that carbon dioxide outgassed from rocks. Scientists don't believe that that's possible on Earth due to our slightly larger distance from the Sun. Okay, there's one last thing we want to do. How would we represent it if an atmospheric layer only absorbed some of the long-wave radiation that hit it and let the rest through? Well, that would make the math a bit harder, but with one layer it's still pretty easy. We'll continue to assume that the atmosphere is transparent to shortwave, but now it'll only absorb a fraction of the incoming long wave. We'll call that fraction alpha. So now when E sub S hits the atmosphere, some gets through, but how much? Well, if alpha times E sub S gets absorbed, then 1 minus alpha times E sub S gets through. Everything else is exactly like what we did before, with E sub A being emitted by the atmosphere and so on. Now our first equation is E hat sub T equals EA plus 1 minus alpha times ES. And our second equation is still ES equals E hat T plus EA. However, solving for EA, we now have EA equals E hat T minus 1 minus alpha times ES. We plug that in to get ES equals E hat sub T plus E hat sub T minus 1 minus alpha times ES. Let's collect ES on the left side by adding 1 minus alpha times ES to both sides to get ES plus 1 minus alpha ES equals E hat sub T plus E hat sub T. Well, that we can factor out the ES to get ES times 1 plus 1 minus alpha equals 2E hat T. So ES times 2 minus alpha equals 2E hat T. ES equals 2E hat T over 2 minus alpha. One thing I like to do when I add complexity to a model is see if I get my old answers with the new model, as that gives me confidence in my math. So let's say that alpha were 0, meaning that the atmosphere absorbed no incoming long-wave radiation. Since it also doesn't absorb long-wave radiation, that's the same as if there were no atmosphere at all for our purposes. Indeed, 2E hat T divided by 2 minus 0 equals E hat T, which is what we got in our model with no atmosphere. What if the atmosphere were fully absorbing? Well, in that case, alpha would be 1, in which case you'd get 2 e hat t divided by 1 equals 2 e hat t, and that's exactly what we got for our fully absorbing atmosphere. Now that I see that in the extreme cases I get what I got before, I'm much more confident that I didn't flip a negative sign somewhere or make an algebraic mistake. In this model, if Earth's atmosphere absorbed about 78% of the outgoing radiation, the temperature would be what we observe it to be, 15 degrees Celsius. If I wanted to be more realistic, I could add more layers and have each one only be partially absorbing. Every time long wave made it through another layer, I'd multiply by 1 minus alpha to find out how much got through. Similarly, I could take into account that the atmosphere does absorb some short wave by not having all of E hat T make it through, but only a fraction. Finally, in a real model, I'd break down the short wave and long wave bands into even more types of radiation and have the absorption and emissions be a function of the real chemical makeup of the layer and the temperature and so on. But that'd take a whole course and a whole lot of computer code, and I think you've gotten what you're going to get out of this model at this point. Though, of course, there'll be plenty of opportunity to have you do some cool stuff on the take-home exam. What I hope you've gotten out of this series is 3 things. First, a real appreciation for how the greenhouse effect works in terms of the atmosphere absorbing and then emitting radiation. Be warned that even after doing all this work, plenty of students still get bad grades on their exams when I ask them to explain in words how the greenhouse effect works, because they talk about energy bouncing back and forth between the Earth and the surface. That is absolutely not what is happening. Energy doesn't change its form from shortwave to longwave when it bounces, only when it gets absorbed and emitted. So don't do that. Second, I hope this shows that it isn't just a lot of hand waving. There really is some basic physics that leads to the effect we're talking about, namely the greenhouse effect. Finally, I hope you can start to picture some of the components that might go in a more complex model of the atmosphere.